Okay, yeah, we're recording. Okay, cool. Okay, so this is going to be final exam spring 2019. Okay, so that's spring 2019 final. Okay. Okay, you have a block of a mystery material, 12 centimeters long, 11 centimeters wide. And 3.5 centimeters thick. Uh, 0.035 meters thick. Its mass is 350 grams. Okay. Now, this is also one of those like, you know, let's just make this like a little bit annoying by doing, by changing the units on you. 350 grams. Okay. Will it float or sink in a tank of water? So that's required. Okay. Float or sink in water. Okay, that's the A part. And then the B part, if it floats, okay, so if it floats, what percentage is sticking out of the water? Out of water. If it sinks, okay, what's the normal force when it sinks to the bottom of the tank? Okay, what is the normal force? When it hits the bottom. When it sits on the bottom, I guess. Sits on bottom. Okay, so in a way, this one is kind of asking almost like, what is the, you know, the B part is almost asking like, you know, what is the weight of, what is the submerged weight of this object, you know, because that's what your scale measures. Right, the actual weight of an object doesn't change whether or not it's underwater or not, but certainly what the scale is going to read if you're underwater is going to change. And that's because what the scale is actually measuring is your normal force and not your weight. Or what force does the scale have to push up to maintain you, to keep you where you are? Okay, so the first part, will the floater sink in water? And what we're doing is we're comparing the density of this object to the density of water. So remember the density of water is 1,000 kilograms per cubic meter. So we just want to know if we're, you know, above or below that. So let's say the rho of the object, okay, is the mass of the object divided by the volume of the object. Okay, so this is pretty straightforward. The mass is 0.350 kilograms. The volume of the object is length times width times height, 0.12 meters. Looks to me like it's going to be more dense than water because these are pretty small numbers on the bottom there. 0.035 meters. Okay, so let's go ahead and, where's my calculator? Let's see what we got here. 0.350 divided by 0.12 times 0.11 times 0.035 equals, oh no, 757.58 kilograms per cubic meter. Okay, so it's not going to sit on the bottom. Okay, it's going to float. Okay, because that number is, because it's less dense than water. And if you wanted to, you could do a force balance there and you could compare the buoyant force to the weight and you would discover that the, you know, so you could compare this if you wanted to. You compare the buoyant force to the weight for a submerged object and determine whether or not it was going to go up or go down. And you would discover that the buoyant force is stronger than the weight. But anyway, so it's going to float. So we want to know what percent of this is out of the water, you know, when it floats. And so, well, we're going to have to do a little free body diagram over here. Okay, and we've got the force of buoyancy going up. We've got the weight going down. Right? And this is, you know, when it's, you know, it's going to be like partially submerged, right? We just don't know how much is going to be above or how much is going to be below. So we'll say the sum of the forces in the y direction equals 0. And we're going to go with, hold on a second. Yeah, so we're going to go with the force of buoyancy minus the weight equals 0. And the force of buoyancy is the gamma of the fluid. In this case, that's water. So I guess we could make gamma of water times the, times the volume displaced, so that's the volume underwater, minus the weight, which is usually it's the gamma of the object times the volume of the object. But I don't want to do it that way because that's annoying for this problem. So I'm going to do mass of the object times gravity because we have the mass. So we might as well do it that way. Okay, so the gamma of water we know to be, what's the gamma of water? 9810 newtons per meter cubed times the volume displaced, so that's the volume underwater, minus the mass, 0.350 kilograms. With gravity, 9.81 meters per second squared equals 0. So we'll solve for the volume displaced. What is the volume displaced in this case? 0.350 times 1 divided by 9810. Wait. What am I doing wrong here? Did I do something wrong? Oh, I got 0.00035 cubic meters. Okay, so that's the volume displaced. And what I want to do, because what I'm looking for is what percent is out of the water. So this is the volume that's in the water. So it would help actually if up here I'd gotten the volume of the object, okay, by doing length times width times height. So go 0.35 times, let's see, clear, 0.0035 times 0.11 times 0.12 equals 0.000462. So this is the total volume of the object. This is the volume that's underwater. Okay, so the volume that's, I guess, out of the water is basically the difference between those two. So minus 0.000035 is 0.000112 meters cubed. Okay. And now what I want is what's the percent that's out of the water. So basically I want to take this and I want to divide by the total volume of the object. Okay, so the percent out equals 0.00012 divided by 0.0014462. So I'm just going to do is the 112 divided by 462. Okay, 24%. 24 points. I'll just give it to you in 3 sig figs like that. Okay, any questions on that? Just a note, if we'd had a different density for this object, like let's imagine I made this thing twice as dense. So now we're like that. So instead of having a density of 757.58, we'd have twice that. 757.58 times 2, 15.2. Okay, if I'd had that, then this would have looked, then the problem would have been different, right? We certainly would end up with a different answer. Instead, it would sink. And if it sunk, we want the normal force when it hit the bottom. And so then at the bottom, we would have the force of buoyancy. We'd have the weight, but we'd also have, the normal force, or F sub n, I guess is probably how it's normally written. Okay, so then what we'd end up with so I'd do plus F sub n equals 0. And this is what we'd be solving for. But the nice thing here is the buoyancy force is fairly straightforward because we don't have to worry about it being partially submerged. So the buoyancy force would be gamma water times the volume displaced, but in this case, it would just be the volume of the object because the entire object is underwater. So the volume displaced and the volume of the object are the same thing, minus mass times gravity plus F sub n equals 0. Okay, so this would be, 9810 newtons per meter cubed times the volume of the object, which is this right here, 0.000462 cubic meters. I cancel it. minus the mass, which is, well, I made it this number right here, 0.700 kilograms. That's 9.81 meters per second squared, plus the normal force equals 0. And so if you were to solve all of that, you would get, well, let's see, 9810 times 0.000462 minus 0.7 times 9.81. Okay. And we'd get 2.33 newtons. Okay, if we go to 3 sig figs. Okay, now note, if you were to get a negative number here, that would imply that your normal force was down, which would mean that you made a mistake somewhere. Okay, because that would mean that basically instead of having a normal force holding it up, you would actually need somebody to be holding this thing underwater to keep it down. So that'd be like, you know, when you try to hold a beach ball underwater or a basketball or something along those lines. So if you get a negative number, either your density calculation was wrong or your interpretation of the density was wrong. Because if I tried to solve this with the earlier number, I would have gotten a negative number for my normal force. And basically that would have meant like somebody needs to hold this thing underwater. Okay, questions? Sorry, I'm starving. Okay. Okay, let's find another one. Let's see. I go to the ones that I worry about with you guys the most. Okay. Maybe I'll do the last one. Last one, and probably, yeah, we'll do the last one, and then maybe I'll come back up and do some HGL, EGL stuff. Just depends on how much time we have. But let's do the last one. Find the flow rate through the cast iron pipe. So basically we've got a system here that looks like this. Okay, so I'm going to need y'all to get to have a what do you call it available to you? A Moody diagram. Okay, so we've got 2 reservoirs. And what's annoying about this one is because there's no pump or anything, we know which way the water's flowing, and it's flowing from the high one to the low one. So it's actually going from right to left, which is not normally how we see these things. This right here is an elevation of 0, and this one right here has an elevation of 10 feet. Okay, the total length of this pipe, L, is 1,200 feet. And this has a diameter of, I think that's given, 1 foot. And each of the bends has a loss coefficient. So each of the bends has a loss coefficient of 0.25. This and this have a K of 0. Okay, because they just decided to tell you to ignore that. By they, in this case, it was me. And then it says, this is a cast iron pipe. Cast iron pipe. And it says this, KS equals 0.012 inches. Okay, so this is an important distinction. This is from when I was teaching this course from an old textbook, or a different textbook. So I don't want you to get confused too much about this KS. This is the roughness length scale. Okay, so your book calls this an epsilon. Okay, but if you see a KS on an old test or an old homework, that's why. It's because there's an epsilon, basically I was just working with a different textbook. All right, so the question here is, find the flow rate. Okay, so required Q equals what? Okay, so it seems like basically, so to me, like whenever I hear what is Q and I know that I have a diameter, then I know that I'm actually looking for the velocity, right? I mean, once I have the velocity, I have the diameter, so I can get the flow rate. So that's no problem. So then my second thought here, well, I've got all these energy losses here. I've got these K values here. I know it's a cast iron pipe and they told me the roughness of it. So they're telling me, they're almost like pushing you into using the energy equation. And the energy equation makes a lot of sense here because because, obviously the flow rate is going to change depending on how much energy is lost between point 1 and point 2. So let's go ahead and do the energy equation. So we're going to go P1 on gamma plus Z1 plus alpha V1 squared onto G plus HP, no pump, so that's nice. P2 on gamma plus Z2 plus alpha V2 squared onto G plus the turbine, there's no turbine, plus the head loss. Okay, so this one's cool because I don't know what it's going to say. Oh, anyway. So there's some nice things about where we pick those points, right? So both 1 and 2 have atmospheric pressure. So those are going to go away. Both 1 and 2 are at the tops of reservoirs. So there's no velocities to speak of, which means we don't have to worry about that alpha, which is awfully nice. There's no pump. There's no turbine. Okay, Z1 is 10. So this is the first number we have to deal with. This is 10 feet. Z2 is 0, okay, because it's the datum. So we're left with this really nice equation, which is 10 feet equals the head loss. So basically we lose 10 feet of energy as we go from 1 to 2. Okay, so let's, so we're going to say 10 feet, or really Z1, but let's just leave it as Z1. Okay, so Z1 equals the head loss, and I'll split the head loss out into 2 terms. So we've got this head loss is going to be head loss due to friction plus the head loss due to the minor. So the friction is FL on D, V squared onto G. Okay, it's all the same pipe, so we don't have to like worry about anything weird going on there. And then plus the head loss due to the minor losses, and so that's going to be the sum of the K's times V squared onto G. So the nice thing here is, we can kind of pull out this V squared on 2G. That's what we're solving for, right? That's what we want. Okay, so I'm left with Z1 equals FL on D plus sum of the K's times V squared on 2G. Okay, now I'm just going to kind of go over that and kind of show you what we know. We know Z1. We know L, the total length is 1,200 feet. We know D is 1 foot. We know the sum of K's, because basically what we're going to do is we're going to say, well, how many of these little bends do we have? I know one of them is 20.25. We've got 1, 2, 3, 4 of them. Okay, so the sum of K's in this case is going to be 1, 0.25 plus 0.25 plus 0.25 plus 0.25. So we have 2 things we don't know. We need F and we need V. Okay, so the problem with this is, I can get V if I know F, I can get F if I know V. Really what I want is I want V. I don't care about F, but I need F to get V. Okay, so that's where this sets up this, there's no other equation for F. So, and I'm going to require you to use Moody diagram for that. But when you go and look at the Moody diagram, and I'm going to pull one up on my screen, you should probably have one out. Let me, Moody diagram. Let's see, I'm going to use the one that's in the wiki page for Moody chart, just because I find it's fairly easy to read. Yeah, so let's see. So when we look at that, okay, to get F, I need to use Moody. So every time I do these problems, I reteach them instead of just. Anyway, so to get F, I need 2 things. I need epsilon over D. Actually, I guess the arrow should go the other way. So I should say like F is a function. Well, F is the wrong thing to be a function of. Anyway, so I need 2 things. I need epsilon, come on. I need epsilon over D, and I need the Reynolds number in order to get F. Epsilon over D is pretty straightforward, right? Because we have this epsilon right here, or this relative roughness. So 0.012 inches, okay, divided by the diameter of the pipe, which in this case is 1 foot, but I'm just going to go ahead and make it 12 inches because I want to make sure this becomes unitless. So epsilon over d is 0.01. Nope, 0.1, excuse me. Okay, so that's cool. We've got that. And then we need the Reynolds number. Well, the Reynolds number equals, it equals the velocity in the pipe, you know, and therein lies the rub, right? That's one of the things we don't know. Times the diameter over the viscosity of the fluid. Okay, so Reynolds number is, let's see, so I guess we're just going to V times the diameter, which is 1 foot, divided by the viscosity. So if you don't know the viscosity, what I highly recommend is you go to Engineering Toolbox. There's almost certainly a chart for this in your book. I don't know the page number, but you know that you have access to the internet for this one. So I recommend going to what are we on page? You know, Engineering Toolbox and just type in viscosity of water. So we're in the imperial units, and if you go down to 50 degrees F, so it should either be at 50 degrees F or 20 degrees C. If I don't tell you anything. It tells you 1.41. 1.41 times 10 to the negative fifth. And that's feet squared per second. I don't even recommend really worrying about the 1.41. If you just did 1 times 10 to the minus fifth, that would be totally fine. Anyway, so we'll solve that and we'll say that the Reynolds number equals, well, 1 divided by, give me 1 second. 1 divided by 1.41 negative 5 equals 70900, and that's units of seconds per feet times V. Okay, so now we've got this triple problem here. Okay, I mean, you probably already knew that this was a type 2 problem, and we were going to have to deal with the fact that our equations don't quite close, or at least not in a satisfying way, right? So if I knew Reynolds number, I could get F. And if I had F, then I could go over here and I could get velocity. Okay, so therein lies the big problem right here. And then I would have velocity. But the problem is because I don't have velocity, I can't get the Reynolds number. So we have to guess. And the way we do this is we always guess, you know, for these problems, you know, it's like, where do you jump in? Do you guess an F or do you guess a V? Or I guess those are the two things we could guess here. We could guess a Reynolds number, I suppose, but that would kind of be the same thing as guessing a velocity. So what we usually do here is we guess an F. And the reason for that is because the range of F's is fairly small. I'm going to get rid of our diagram, which is really quite horrible, because I hate to not think about what it is that we're working on, but I don't really have much whiteboard space here. So goodbye. Okay, so I guess what we need to do, one thing we need to do is, I'm also going to solve this equation right here. So Z1 is 10 feet. Okay, L on D, well, the length was 1,200 and the D was 1 foot. So this is going to be 1,200 F. Okay, the sum of the Ks, well, that's just going to be a number 1. And the 2G, well, 2 times gravity in the metric system is 64.4 feet per second squared. Okay, so let's go ahead and solve this thing so that it makes some sense. And I will ask you guys to bear with me. So what I'm going to do here is I'm going to guess an F, okay, assumed. Okay, so that's going to go into here. Okay, and that's going to solve for me and give me a V. Yeah, that's going to be from this equation right here. Okay, so that means I want to solve this equation for V. So this is going to be V equals the square root of what, 64.4 times 10, which is 644. 644. That's feet squared per second squared over, I guess 1 plus 1,200 F. Okay, so that's going to, this is equation 1. Okay, unless I made an algebraic error, which is, of course, my forte, right? All of our fortes, we all make algebra errors. Okay, once we have that, this is still basically just a guess for V. So then we're going to go to the Moody diagram here. I'm going to calculate the Reynolds number. That's equation 2. Okay, and then we're going to get our F from Moody. Now, some of you will try because your book likes to use the Colebrook equation. You're not allowed to do that in my class because you're not allowed to do that for the FE unless you've somehow memorized the Colebrook equation, which is a really nasty equation. So I don't recommend trying to do it that way. All right, so now we need to figure out which value we're going to guess. So epsilon on D in this case is 0.001. So hopefully you guys are doing this where you guys are sitting. But if you look at 0.001 relative pipe roughness and you start on the right, and you're just going to follow your ruler all the way to the left. And I'm going to get a number pretty close, just barely below 0.02 for my F. I could make it 0.019 for my guess if I want, but I'm going to make my guess 0.02 because I just want to be easy, right? It's just a guess anyway. So from this point on, you're just if you're solving this, you're just a machine. Okay, so I'm going to go, okay, well, let's see, 0.02. So I'm plugging in here, 0.02 times 1200, okay, equals, I'm going to add 1. Okay, raise that to the -1 to get it on the bottom, multiply it times 644, raise that to the half power. Okay, so I'm getting a velocity of 5.0754. Okay, that's feet per second. Feet per second. Okay, I'm going to plug that in here to get a Reynolds number. So multiply by 7,900. And I get 3.6 times 10 to the 1/5. Okay, so now I'm going to go to the Moody diagram. I'm going to follow that blue line, the 0.001. I'm going to follow it until I get to a Reynolds number of 3.6 times 10 to the 5th. Okay, so 1 times 10 to the 5th, 2 times 10 to the 5th, 3 times 10 to the 5th. It looks like we're at 0.021 is about what I'm seeing. 0.021. Okay. After I've done with the problem, I'm going to pause and make sure that you guys can all see that because that you guys are getting those numbers from your Moody diagram. Because it's a definite skill. Okay. By the way, I wouldn't try to go more detailed than 2 sig figs here. It's simply not really that possible with the chart. Now, if you do it with a computer to solve the equation, you can get pretty exact. Anyway, so I'm gonna plug it back into here. Okay, I'm gonna add 1. Put that on the bottom by multiplying by -1, or raising to the -1, multiply by 644, take the square root, and we get a number that's not that different, 4.9578. Okay, we're gonna plug that into the Reynolds number. Almost certainly we're gonna get almost the exact same number, Reynolds number, at least the 2 sig figs. 3.5 times 10 to the 5th. And I'm not going to be able to tell those differences on the Moody diagram, so this is going to be the same. Okay, which means this is our velocity. Okay, and so then because we want Q, we're going to say Q equals V, 4.9578 feet per second, times the area, pi on 4 times 1 foot squared. Okay, I mean, it's a little bit sloppy, but I'm not really, don't really have a lot of space here. So that number times pi divided by 4. Okay, to 3 sig figs, 3.89 cubic feet per second, CFS. Okay, and that would be the final answer. And I just hope that matched what I got when I did the exam. It's probably off a little bit because when I do the exam, I solve for the friction factor. I solve the Moody diagram numerically. So I'm going to get a much more perfect answer. Anyway, how'd y'all do with the Moody diagram on that? Did y'all do okay? Paul, did I see a head shake? You're good? Okay. Alvaro, same? You okay with the Moody? Okay. So just, be prepared for that. And it's going to show up on the FE almost certainly. So just be aware of that. Actually, I say that. I only took the FE once. Never mind. I can't be that short. But I know that they give you the Moody diagram for the FE. They do not give you the Colebrook equation. So, the Colebrook equation is nice, but you also need a fancier calculator, or, you have to figure out how to solve it. Kind of annoying. It's an implicit equation. So just be aware of that. Okay. Any questions? Hopefully this process is becoming I've now made oodles of videos on this, but hopefully the process is becoming a little bit more clear why it is the way it is. It's a little bit unfortunate, right? It's not very pleasing. Hold on, let me turn the fan on here. Okay. So I'm going to clear all drawings. Let's see what else we got on this here test. I'm not going to do number 6 because I've worked problems like that one a million times. I might even already work that one for you guys. Okay. I love it. I'm going to do number 3. The hardest thing for me when I took this course was definitely momentum equation. For most of my students, really hate the forces on the hydrostatic forces. But for me, it was definitely momentum equation. So anyway, it's got this cool thing. So this is number 3 from that test. And let's see, we've got a pipe doing this, and it's turning, and then it's going down. And actually, I shouldn't draw it like that. Let's see, yeah. So anyway, so we've got a 12-inch pipe here, 12 inches, and we've got an exit here that's only 6 inches. Okay, and we've got the fluids going out here at B2. It's going in here at B1. I will note that if I've drawn this properly, you will be able to tell that that V2 is exiting into the atmosphere. Yeah, okay. It says in the thing, the nozzle discharges into the atmosphere. Okay, it's a key point, right? So that we, so this is all water. And this is X, and this is Y. Determine the magnitude and direction of the X component of the force required to anchor the horizontal bend, and nozzle shown below. Okay, and then so right here, there's some sort of anchor thing, a flange or whatever it is that's holding this thing to the wall or whatever it is. Okay, and they actually tell you that this is section 1. And they tell you that the pressure at 1 is 15 PSI. I do not work in PSI, so let's multiply that by 144. I guess there are times I work in PSI, but I don't like to. PSF. And then V1 is 5 feet per second. Okay, and note that this is horizontal. Okay, so X is flat and Y is flat, so there's no gravity in this problem. So this is what's given and required. Determine the magnitude and direction. So force to anchor this in the X direction equals what? And we could do the Y direction here, except the Y direction is completely trivial. There's no forces in the Y direction. There's no momentum. So the Y direction is 0. So my free body diagram is going to be like this. Well, I guess it technically does not include the flange itself. Okay, because the force of the flange is on the water. And I don't know if it's going to the right or the left, but the force of the flange is on the pipe. That's the anchoring force. Okay, so maybe we can draw the forces here. So I'm only going to draw X because that's the only direction there is really. F anchor X. And really that's happening where this flange, you know, acts on our free body diagram. But I'm going to draw it over here just because I like to have it kind of in the middle. Okay, we've got no gravity in this thing because it's all horizontal. I've got some pressures. I've got a pressure here. So that's P1A1. What else do we have? We've got some, so this is a momentum flux, V1. And I've got a momentum flux here, which is V2. I always like to draw those across my boundary so that I know that I have those. Okay, and I think that's everything. So in some ways, this is a nice momentum problem because we don't have any angles and we only have one pressure and we don't have to do any Bernoulli to get a pressure. So, you know, this is pretty good. So we'll do sum of the forces in the X direction. Plus in rho VQ in, I guess this should be a summation, equals summation of the momentum fluxes out. Okay, so the forces in the X direction, we've got F anchor in the X. Okay, let's see here, plus P1A1, that's in the positive X direction. And is that all the forces? Yeah, it's pretty easy. And then, because there's no P2A2 because that's going out into the atmosphere. Yeah, so then what else do we have? We've got, okay, so we've got a momentum flux in, which is going to be rho V1, which is positive, times Q. That's pretty straightforward. Okay, equals, well, we've got an out, which is going to be rho. Well, V2 is negative, so it's going to be negative V2, and that's going to be Q. Okay, and that's it. So that's how we're going to solve this. We're just going to plug in for all of that. What I'm going to do in this case, in order to make this, at least to me, seem easier, and this is common things that you'll see, F anchor X, plus I'm going to leave it as P1A1, and then rho, and this is, I'm going to change into V1 squared A, because I'm going to turn that Q into V1A1. Okay, and then over here I'll get equals rho, negative rho. Let's just do this. Let's bring it over to the other side. Plus rho V2 V1A1. Right, so I could do it that way if I wanted to. Okay, and this way I've only got one area that I have to calculate. I've got two velocities I got to calculate. That's a little annoying. Right. So actually, we don't know V2. Well, we do know V2. V2 is fairly straightforward. Let's go ahead and do the numbers on the side here. So we need A1 is pi over 4 times what is that, 1 foot squared. So that's pi over 4. Okay. P1 is given. A1 V1. V1 equals. Well, actually, we don't know V1. Oh, we do. It's given. Sorry. All right, so V2 equals Q over A2, and Q in this case is V1A1 over A2. Okay, and we know the ratio of the area of 1 to the area of 2 is 4, right? So V2 equals 4 V1. Okay, so that equals 20 feet per second. I'm sorry, this is feet squared. Okay, and I think that means that this is just a plug and chug now. Okay, so F anchor and the X equal, plus P1, which is 2160 PSF times the area, which is pi on 4 feet squared. So that gives units of pounds, plus rho. The rho of water is 1.94 slugs per cubic foot. Oh, we hate those units. Okay, V1 squared, which is 5 feet per second squared, and A1, which is pi over 4 feet squared. Okay, so before I continue and get the next term here, let's just go ahead and check the units on that one. Okay, we've got, so right here, we're gonna have feet squared times feet squared. So it's gonna give me feet to the 4th on the top. There's a feet cubed on the bottom. It's going to go with a feet on the top. I'm going to put the slugs on the bottom. And I have second squared right here. Okay. And if you're unfamiliar, we have to think back to mass times acceleration. Okay. So basically this is mass. This is acceleration. Okay. And so that does in fact give us a pound. Okay. So we're good here. Okay. It's ugly, but we're good. Okay. So just always a good idea to check yourself on that. Okay. And then we got to do this term, which in this term will work out units wise because it's the same thing as what we had right there. So I'm going to say plus rho 101.94 slugs per cubic foot. Okay, V2 times V1, so that's 5 feet per second times 20 feet per second. And then area pi on 4 feet squared equals 0. Okay, notice based on all of these that the F anchor is going to be negative. Okay, and I'm going to go ahead and I'll just plug all these numbers in real quick. Times pi divided by 4 equals. Go. So this one is 1696.5 pounds. Okay, this one is 1.94 times 25 times pi divided by 4. This one is 38.092 pounds. Okay, and this one is 1.94 times 100 times pi divided by 4 equals 152.37 pounds. Okay, so clearly in this case, the pressure is the dominant term. Okay, so negative 1886.7 pounds. F anchor X equals negative, or you know what, let's do it the statics way. All right, I guess 1.89 kips in that direction. Okay, pretty cool. Any questions? Okay. Let's see, we've got 25 minutes. Is there anything in particular, any other thing y'all might want to see? Let's see. Okay. Well, I'll keep working. Okay, rectangular gate. So we'll do a gate problem. Yeah, let's do a gate problem. Okay, rectangular gate having a width. So this is number 5. So we've got some water and it's being held back by a rectangular gate with a hinge right here. And here's the gate. And there's a force right going this way, P. So this is the gate right here. And this is all water. Okay, the width of this thing, which is usually written as a B, is 4 feet. The gate is hinged along its top edge and held in position by the force P. Friction at the hinge and the weight of the gate can be neglected. Find the required value of P. Okay, this is 6 feet. This is 10 feet. It goes to the and this is 60 degrees, 60 degrees. Okay, So let's see what we got here. By the way, one thing to expect in this case is if I give you a large number here, you can expect, like this one's 4 feet, but if I give you like 50 feet or 500 feet, or I made it really, really wide, you can expect humongous numbers in these problems. Just something to be aware of. All right, let's go ahead and label some things here, just because we're here. Okay, this is a rectangular gate. So this is going to be the H to the centroid. This right here, that's going to be the Y to the centroid. And then similarly, there's going to be a point right here somewhere, and that's going to be Y to the center of pressure. Okay? And that's really the thing that we need. And the reason we need that is because that's where the force is going to act. So if I do a free body diagram, which I kind of like to do these early anyway, of the gate, okay, it looks like this. Okay, we've got these forces on the hinge, Hy and Hx. I've got a force acting here, which is the force of pressure. And then I've got a P acting right here. Okay, this is 6 feet. And this distance right here is going to be the YCP minus that 10 feet. Okay, so like right now, like I can already line this problem up. I know where I'm going to end up. Okay, I know I'm going to sum moments around that hinge. I know I'm going to end up with the sum of the moments around the hinge equals 0. And I know that F of P times YCP minus 10 feet, okay, that's going to be going counterclockwise. And then we're going to subtract off the P times the 6 feet equals 0. Right, so I already know that this is where we're going to go. Okay, but the problem is, of course, I don't know YCP and I don't know FP. So those are the things that we have to solve for. So let's go over here and let's consider our shape. So our shape is a rectangle. Okay, so like if I was swimming in this water and I were to look at this thing, I would see a rectangle and it's 4 feet wide. And depending on the angle that I'm looking at it, right? So if I'm looking at it at this angle, it's going to look like it's 6 feet tall. But if I'm looking at it at this angle, it's going to look like, it's whatever that height is. I guess the height going up to here, right? So it just kind of depends on what angle I'm looking at it. But the shape itself is actually 6 feet tall by 4 feet wide. Okay, so it is actually 4 feet wide by 6 feet tall. Okay, so the area of that thing is 24 square feet. The H sub C, okay, the depth of the centroid, and then we'll get Y sub C after that. But H sub C, well, let's see what we've got here. Let's use like, I don't know what color do we have left here? Let's use some green. So the H sub C is, well, actually, you know what? The Y sub C is really easy to get. 3 feet, 10 feet, 13 feet. Let's do black for that, 13 feet. Okay, so now we've got a nice triangle here between the Y sub C and the H sub C. And we use a little trig in the fact that this is a 60-degree triangle right here, 60-degree angle. So let's see, what is that? So that's HC, well, let's not do this. We know it's the sine because it's the opposite side. So we want the sine of 60. So katoa, so the opposite side is H sub C over the Y sub C, which is 13 feet. So the H sub C equals 13 sine 60. 13 sine 60. Okay, 11.258. 11.258 feet. Okay, so then the last thing we need is we need the I bar, or the, excuse me. I guess it depends on different books, will write it different ways. The moment of inertia around the centroid of that object, which I don't know. I'm just gonna write it as I bar. Okay, X is fine. All right, so equals 1/12 the base of that triangle times the height of that triangle, of that rectangle cubed. So 1 divided by 12 equal equals times 4 times 6 cubed, 72. And that's feet to the 4th. Well, this one's nice. It's got nice, easy numbers. All right, we like easy numbers. All right, so once we've done that, now I just need to figure out FP and YCP. And we can almost do those without even thinking. The only thing that we really need to remember is that YCP is going to be larger than YC. So if I get something for YCP and it's not, 13.7 or 14 or somewhere in that range, probably think we made an error, right? It also is not going to be larger than 16 because it's going to have to be on the object. So the force of pressure is gamma HPA, and the YCP equals YC plus I bar over YCA. So at this point, it's just plug and chug. FP equals gamma. So in this case, that's 62.4 PCF. HP, HC, which is 11.258. And the area is 24 square feet. Okay, so FP equals whatever that is. Okay, we get a pretty big number, which is not unsurprising, 16,860. Okay, and that's pounds. Okay, and again, we've got feet cubed, pounds per cubic foot, so we get pounds. So we're in pretty good shape here. Okay, and then, well, of course, I did a poor job with my space as usual. So YC is 13 feet plus I bar, which is 72 feet. YC is 13 feet, and the area is 24 square feet, feet squared. This is feet to the 4th. So we've got feet to the 4th divided by feet cubed. So we're going to get feet for that. So YCP equals 72 divided by 13 times 24. Okay, that's a pretty small number. So we're going to get 13.231 feet. Okay. So now we're going to go up to the sum of the moments, and we're going to just plug in some numbers. Okay, and notice this number is just barely bigger than 13, which was the expectation. Really, on a rectangle, it should be somewhere between 13. It should be somewhere between half of this distance, so that would have been 13, and 2/3 of this distance, which would have been, in this case, 14. The 2/3 would have been if this thing had been at the surface, but it's not at the surface. The deeper you go, the closer it gets to the centroid. Okay, so here we go. We're going to get 16,860 pounds times YCP minus 10. So that's 3.231 feet minus P times 6 feet equals 0. And so P equals 16,860 equals 9,078.5 pounds. Okay, and if we want that with 3 sig figs, we should say P equals 9.08 kips. Okay, and that's it. So questions? I feel like I've been talking to myself. You guys have been so quiet.
I have a question, not about this, but about the exam.
Okay.
So are we going to have like a separate Zoom link, or are we using like one of these?
Yeah, I'm going to send you a link.
Sounds good.
It's low on my list of priorities, and if I send it too early, then people lose it. So, although maybe I should send it early and late. Early so that people can relax and know that they've already received it, and late so that if people lost it, they can find it. But right now I owe you guys a bunch of grading, so I'm really more concerned about that. I had to finish up my statics class. They didn't give me a, for some reason, they scheduled my statics class during a slot that was not given, like, they didn't give me a final exam slot for my statics class, which is super annoying because it meant I had to try to schedule a final for 29 people, which is impossible. Whereas if the university gives me a time slot, I can just say to people, well, you figure it out, because that's when it's going to be. And so I made it on the last day of class. So unfortunately, I've been grading like the Dickens to make sure, and creating a final and sitting there and, you know, all that. So, yeah, so, but it's still no excuse. I'm really behind on grading for you guys, but not for them, because I had to get it, you know, everything ready for them. Yeah. Anyway, I've already been quiet. How are you?
Good. I'm good. I'm trying to study up.
Yeah. Finals week is upon us.
Yes, sir.
The best and worst week ever. Best because every day you kind of like, you're like, oh, one more class is in the books.
All right.
As long as you're not like in danger of failing anything, you know.
I mean, that's a plan.
Yeah, it's really nice when you have that, like, I don't know, when all of your class, like if you have a class you have like a mid B on, and you're like, well, I can't get an A, and I would have to like bomb to get a C, so I can relax about this class, you know, or mid A, you know, whatever. When you're so situated that like really like the grade's already written for you. Anyway,
I know you said you're real busy, but do you think you'll get us the test 2 before the final, or?
Oh yeah, absolutely. That's going to be my whole day today. Well,
Okay.
minus office hours, you know. So I'm going to break to run, and I'm trying to stretch every 2 hours because I'm sitting in front of this desk. I'm sure you guys are too. My back is starting to go out on me, you know. I think this chair, aside from the squeakiness, is actually okay. But anyway, let's look at one more before we go. Unless y'all have more questions. Sorry, I'm not trying to shut y'all down, but
That's fine.
okay. Okay. So actually, I think maybe let me see if I can share my screen here. Let's share screen. Okay. Start broadcast. I got you. Oh, there it is. Okay. Good. Okay. I want to go to. Oh wait, here we go. Safari. Oh yeah. You get to see the things that I'm looking at. Oh yeah, this Reddit tab. I just love parkour. I wish parkour had been around. I'd been aware of it when I was like 16. Like I watch these videos and I get so excited. These guys in London race the tube. It's like 7 minutes and them running. Like they get off at one stop of the subway and they run up and then they like parkour across the city and they barely make it to the tube and the other thing. It's so cool. Anyway.
Did you ever see the movie District B13?
No.
It's a French parkour movie. It's awesome. You should check it out.
District what?
District B13.
Okay. Done. I keep meaning to ask you guys like for things that I should check out. You know, like that should be like a bonus question. Like, you know, what song should I listen to? And if I like it, you get a point.
Works for me.
Okay. Let's see what we have here. Come on. Come on, you can do it. Let's see, assignments. Oh no, old exam and quizzes, sorry. So I just didn't want to draw this one. I guess I could have been doing this the whole time, couldn't I? This one. This is the one we've been working on. Oh, yeah, so this one. All right, so I just kind of wanted to talk about this because I don't want to draw an HGL, EGL. We're kind of low on time, but I really like this one. It's got some weird things going on here. Okay, the HGL and EGL for a pipe system are shown in the figure. A section is not shown, so I just cut out a bit of it. Okay, so like you can see, let's see, can I annotate here? Oh, I can't annotate, I guess. That sucks. All right, anyway, you can see that between B and a little bit to the right of it, some of it's been missing. Okay, so the pipes are not necessarily drawn to scale. It's a little annoying. Okay, which one's the HGL? Which one's the EGL? Can y'all tell me?
The EGL is the top one, right?
Yep, EGL is always above the HGL. Okay, so basically, you just, to get from one to the other, you just subtract V squared on 2G. Okay, are the pipes the same size? If not, where's the smallest pipe?
No, they're not the same
Or how can you tell?
because the slope is different from A to B to B to C, but from B to E, it seems like it's the same diameter.
Yeah, so from B to E, it's, well, the same diameter until right before E. So you see the distance between the two lines, which I can't really draw because for some reason I can't annotate on this thing. Maybe I can. Oh, no. Anyway, so the distance between the two lines is the V squared on 2G. So you could almost think about the distance between the two lines as being the inverse of the size of the pipe. So where those two are close together, you've got a fat pipe or a wide pipe. Where they're far apart, you've got a narrow pipe. So from A to B, you've got a narrow pipe because V squared on 2G is fairly large. And then from B to all the way until, right before E, you've got a really, really wide pipe. So it's narrow to B and then wide from B to right before E. Now you see something weird's happening right before E, and we'll talk about that in a second. Okay, so the smallest pipe in this case is from A to B. Yeah, from A to B, because we have the largest V squared on 2G. Okay, are there any regions in the pipe where the pressure is below atmospheric pressure?
I'm gonna go ahead and say no.
No. There is, in fact, a region where we're below atmospheric pressure. And this will be a really useful time for me to be able to write. Let me see here. Okay, so, all right, so imagine a line running from A to B to C to D to E. So it's just following down the middle of this pipe. Okay. That is showing the points that's all the points in our system of the flow. Okay. So there's a datum somewhere underneath there. So the datum, so let's suppose we go to A, right? So we've got a line from our datum to A, that's Z. Okay, we've got a line going from A to the dotted line, that's P on gamma. And then there's a line from the dotted line to the solid line, that's V squared on 2G. Okay, so if I go to, I don't know, point D, right? Same thing, we've got a line going from our datum to D. Okay, and that's Z. And then I've got a line going from D. Oh, actually, that's pretty helpful. I didn't mean to do that, but I've got a line going from D to the dotted line. And that's our P on gamma. And then I've got a line going from, the dotted line to the solid line, and that's V squared on 2G. So basically P on gamma, our pressure is always going from Z to the dotted line. And so when I say, is the pressure ever below atmospheric? What we're looking for is a point where, is there any point where we're going from Z down to the dotted line? Because that means we've got a negative P on gamma. And if we have a negative P on gamma, that means we've got a negative pressure. And a negative pressure, because we're working in gauge, means it's below atmospheric. So you can see that so hopefully you can see, based on what I just said, the pressure goes negative a little bit before B, and it stays below atmospheric until somewhere between C and D. I don't know. I guess y'all can't see my mouse. Can you see my mouse? No.
No.
Okay. Does that make sense to you guys?
I got you.
I'm a little bit lost, to be honest.
Okay. So let's suppose I wanted the pressure at A, right? So we have three quantities, P on gamma, Z, and B squared on 2G, right? You with me? Okay. So Z is just going to be from the datum to A, right? P on gamma is going to be from A to the dotted line. So you can see that P on gamma at A is positive and it's fairly large. Can you see that? Okay, and then V squared on 2G goes from the dotted line to the solid line. Okay, so now if I move somewhere between A and B, right? Notice the Z is the same because I'm still going to go down to the datum, so I'm still at the same elevation. The V squared on 2G is the same because the distance between the dotted line and the dashed line is the same. But P on gamma is now maybe half of what it was earlier, right? And so you see, as I move along that pipe, the pressure is getting less and less and less until I get to the point where the dotted line crosses the pipe. And at that point, the pressure is 0. Okay, because Z is still the same and V squared on 2G is the same, but there's just nothing, there's no space left for the pressure, right? And so now it's 0. And if I keep going to the right, it keeps dropping. The pressure keeps dropping. And so it actually goes negative. So the V squared on 2G, like right before B, let's say right where they cut the pipe, the V squared on 2G is still the same as it was between A and B, like that whole section. The Z is still the same, but the pressure is now negative. So basically the pressure is just dropping the whole way from A to B, and it went from like being really high until it actually got negative. Okay, so basically anytime you want P on gamma, you're just going to basically go, okay, where is my Z? Where's my elevation? And then you're just going to draw a line from your elevation to the HDL. And if that line goes up, you have positive pressure. And if that line goes down, you have negative pressure. Does that make sense? Okay, so we end up having negative pressure from that point where the dotted line crosses between A and B. And we have negative pressure all the way along until that spot between C and D where the HDL crosses the pipe. Okay, everywhere else, so we've got this huge area of negative pressure.
Right.
Now, if it doesn't cavitate, we don't care. So we'd have to be able to figure out if it cavitates. The other reason we might care about negative pressure is it means instead of the pipe pushing out on the walls, or instead of the pressure difference being net outwards on the walls, now the pressure difference is net inwards on the walls because there's more pressure outside than there is inside. So your pipe might implode, or it might just close in on itself. So if it was made out of like some soft rubber or whatever, you might have a pipe just implode, which would be, I don't know, it would just kind of fold in on itself. No big deal. All right, let's see here. What do you think is located at point B?
An abrupt expansion?
Yes. And we know it's abrupt because you see the head loss happens all at once. Like right at B, we lose energy. So when we lose energy, so basically the EGL drops precipitously. So we know we've lost energy. And it's all happening at one point, so it's got to be abrupt. If it was happening kind of slowly petering down, then there might be like a smooth transition, but we don't have a really smooth transition here. The other thing we know is that the pressure went up, the HDL went up, okay? And the V squared on 2G went down. Okay, because the distance between the HDL and the EGL went from big to small, which means the velocity decreased greatly. And so for the velocity to decrease greatly, there's got to be an expansion of some sort of the pipe. Var, you all right with that? Okay. All right, let's see. Where's the point of maximum pressure in the system? So we just kind of talked about that a second ago. So where's the max pressure? We're looking for where is P on gamma the most positive?
At A.
At A, right? Because the distance between Z and HDL is as large as possible. So, you know, that's where P on gamma is maxed. And then what's going on at E?
Is that a gradual expansion to a reservoir?
No. Okay, a few things. Well, let's start with, so what is the pipe doing? So V squared on 2G is doing what? Getting bigger or smaller?
Bigger.
Bigger. So if so that means the flow is accelerating. So if it's accelerating, what do we likely have?
Oh, then it's probably like a nozzle.
Yeah, it's a contraction or a nozzle or something along those lines. It's getting smaller. All right, so then what's the pressure at E?
Zero.
Zero. So it's not going to a reservoir. What's it doing instead?
Just going out into the atmosphere like a jet.
Just going out into the atmosphere like a jet. Yeah. And the other thing to remember, that one of the ways we know it's not a reservoir is with a reservoir, the HDL and the EGL are at the same location. So if that would have happened, so notice we still have a V squared on 2G, you know, because from E to the EGL exists, or really from the dotted line to the solid line still exists. So we still have a V squared on 2G. We just, you know, we just don't have any more pressure. So because we exited to the atmosphere. So anyway, so that's how we think these things through. It's kind of, it's a tricky process, you know, and it's sometimes it's like, it makes you think backwards, but the key really to me is always just thinking about the V squared on 2G. That's the number one thing, is the V squared on 2G.
So an HGL EGL problem would look like this if we had one.
It could, or I could ask you to draw one or the other. I like these because they're easy to grade, but I can't, like I have to find these, like I have to search the internet for these. Like I've tried to create these in my head and I can't. Like there's just something like, I don't know. So maybe I'll try, but I might have used all of these already. So, you know, guys, if you guys were in class and I don't know, but like this, I think if I gave you this, you could probably do a image search for this and just get the answer. I don't know if that can be done. I'm sure it can be done, you know. Anyway, so I usually just tend to instead have you draw one. And then there's like, if I have you draw one, there's usually, I'll find 10 things on there that I want to see, which is tedious grading, but you know, grading is tedious. So what do you do? Anyway, that's all we have time for. Any last questions? I will have, I'll be in regular office hours this week, and probably over the weekend, I'll probably have 2 emergency office hours. Just, you know, I'll probably do one Saturday, one Sunday. I think the exam's Monday, right? I haven't looked it up yet.
I think it's Tuesday.
Oh, Tuesday. Oh, cool. Well, then that'll save my weekend a little bit. Maybe I'll do one Sunday and one Monday then. You know, but basically the 2 days beforehand, I'll try to have I'll do emergency. You know, if you have emergency questions, so that you know, so you're not sitting there going, oh my God, like, you know, I didn't make office hours on Thursday because I had so many other things to do. So anyway, or maybe I'll do 2 Monday, one Monday morning, one Monday evening. That's probably a better option. Anyway, if that's all you got, then I'll see you guys later. Thanks for the semester, and
Thank you.
I'm sorry I won't see you guys again.
Appreciate
Thank you,
you.
sir.
All right, see you guys.